Everybody knows Apostolos. And if you don't know him, you know him by now.
Yeah, I have a slide about that. For people who might not know me. Okay, welcome. So, yeah, given a rather, I mean, I thought about it a few minutes ago, and I thought, wow, I couldn't have chosen a more general title for this talk. But in fact, you know, I'm not going to, of course, talk about everything that is related to chemistry, climate, processes, and how to examine them. But because of the fact that this particular study and its results, we actually hope to use them, to use it as a guide, as a pilot for other studies related to processes in the troposphere and interactions between chemistry and climate. This is why I gave this title. The main thing I'm going to talk about is one aspect which is related to the correlation of two important species, ozone and CO, in the troposphere, from satellites and from models, which is part of this series of things that we want to do related to this kind of framework. So this is the introduction thing that I said earlier. So for anyone who might not be very, very familiar with what I do, there is these two different kinds of areas that I'm working on. This kind of started when I came to GISS, and it's more related to climate forcing response relationship, in particular regional climate sensitivity and trying to constrain it. There is a paper which has already been published on this, and we want to take it further. And actually, this is the other talk I gave in this lunch seminar maybe 1.5 years ago. But my main area of interest has been and remains this one, which is chemistry-climate interactions. So, broadly speaking, is how, you know, certain species in the atmosphere, especially in the troposphere, change in time and space, and how emissions, but also climate and meteorological variability might affect it. We also study the other way around, like how these changes affect climate in turn. But in particular, this work that I'm going to present is related to the first kind of thing. And there have been several papers related to this kind of area, and I would say this talk is related to this as well. So I mean, this, I guess for you is very basic, but I thought I would keep it because it's rather fancy. So it kind of shows all the interactions that happen in the atmosphere and have relevance to chemistry. So of course a lot of emissions of different kinds, but the problem that we really are interested in is what happens to these emissions as soon as they go into the atmosphere. There's a lot of interactions, there's a lot of gases that go into chemical processes, reactions with light, photolysis as we call them, and then there's a lot of interaction between aerosols and gases, and then they have effects on climate, and climate in turn has effects of course on the gases and aerosols again. Interactions with the stratosphere, interactions with clouds, and all these things we have incorporated into our models, and that's a fairly new thing. I mean, like 20 years ago, there were GCMs, there were some maybe initial chemistry models on a global scale, but now we're putting all these things together. So we have models which include aerosol gas interactions, interactions with climate, stratosphere, troposphere, unified, and all this kind of stuff. And of course, we have many new measurements as well, especially in the last 10 years, for example, from the NASA A-train satellites, which focus on these particular species that we care about, like CO, ozone, NOx, aerosols, which have relevance to atmospheric chemistry and climate studies. So as I said briefly earlier, this particular study is about studying the correlation between ozone and CO in the troposphere. And first of all, why is it important to know things about ozone and CO? Why is it important to understand? More or less, you're all familiar about the fact that they're important pollutants, toxic, and especially ozone, apart from humans, it has effects on plants as well. The other thing, which is a little bit more complicated, but still very important, is that they affect what we call tropospheric oxidation very, very much, in indirect and direct ways. Tropospheric oxidation is the process how many species in the troposphere, pollutants or climate-relevant species, get removed because of reactions with what we call oxidants. The major oxidant in the troposphere, what we call the detergent of the troposphere, is the OH radical, the hydroxyl radical, which removes CO itself. It also removes hydrocarbons, removes methane. So CO, because it is removed by OH, it consumes OH, so it in a way determines the levels of OH in the troposphere. The more CO you have, for example, due to fires, the less OH you have available for other species to be oxidized. On the other hand, ozone itself is an oxidant, less important, but still it is. And it's the major source of OH, this most important oxidant that I said earlier, because when ozone is being photolyzed, it breaks down and it usually produces OH radicals, which then are, it's actually the main source of OH radicals. So with that, I kind of telling you that they're very important, both of them directly and indirectly, for these oxidation processes. And these oxidation processes, apart from chemistry, they have relevance to climate. So those two, they both have relevance to climate. This one directly because it's a greenhouse gas of a certain importance, tropospheric ozone I'm talking about, right? And both of them because they affect OH, as I said, and OH generally affects several things like methane. It's the major sink of methane in the troposphere. It also affects aerosols because the oxidation, for example, of SO2 can lead to sulfate production. So you have a lot of things that have implications in climate that have relevance to those important species that are usually known for their pollution impact.
Can I ask, just is there, I should know this, but I don't, is there a particular affinity of OH for CO versus methane versus other?
I'm a little bit unknowledgeable about the word affinity.
Oh,
So
meaning, is there a greater chance, if there's all these other gases that are in a
that one of them survives?
well, is there a greater chance that some will react with OH before others will?
So
Am I asking this the right way? Yeah. So if there's
you're asking about the
if
reaction,
there's
the
met-
reaction rate.
Thank
is-
you.
yeah.
But I mean,
But
if
it
there's
could be co-location or something too.
yeah, but let's say methane is sitting there and CO is sitting there and
Yeah.
OH is sitting there. Any chance that OH
No.
would react with methane before OH or CO before
Actually,
methane
that, I mean,
no or none?
I'm not sure. I mean, it's a matter of the reaction rate, as Costa said. So these are the kind of things that they study in the lab, you know, and they try to find what is it. And then we use these reaction rates tabulated in our models. So I mean, it could easily be checked. But again, this will be very dependent on other things, like temperature, like, you know, maybe humidity that's around. So even though you may look at the reaction rate and get a sense of which one could be faster removed under the same conditions or something, certain conditions, then on a global scale or at different regions, and that's why we use the models, you know, to try and examine these variations, you know. So, so yeah, apart from being important species, they also have a lot of relevance, not relevance, but interest, because they have complicated processes that affect them and make them their distribution around the globe. So first of all, their lifetimes are kind of in between other species' lifetimes. They're kind of intermediate. They don't have a very long lifetime for them to be very well mixed, and they don't have a very short lifetime for them to get stuck over a certain area. So they have this intermediate kind of lifetime, which makes them have very interesting structures in the troposphere. And one of the reasons is this, why they do have a very complex distribution. So the chemistries are also interdependent. I probably said earlier that CO is a precursor of ozone, so it can produce ozone, and I'll analyze it more later. And generally, we understand some of these processes, and we've made a lot of progress in understanding them, but there's still a lot of challenge in trying to explain many of the variability that we see. It's not that we understand everything, we're far from that. It's, for example, far from what we know about stratospheric chemistry processes, for which we pretty much know what's happening. In the troposphere, we know some things, but there are many undiscovered things yet. So, I mean, in this case, we hope to use the satellite products, which now are abundant. We have different species and stuff, which wasn't possible several years ago, in combination with the model. And the purpose is not just to look and compare concentrations, like, hey, how's the model doing in terms of CO or ozone in terms of concentration, you know? Does it compare well with the observations? But we also want to do some correlation analysis and sensitivity studies in order to see what the underlying processes can be. Because ozone and CO, ozone depends to some extent on CO in a very complicated sense. So, I mean, what's the correlation? How does it differ from place to place? What could be the reasons why this correlation may be changing? So in a way, it's like a process-oriented evaluation of the model. So a few things about the budget of CO and ozone, what determines it, very briefly. I'll say that, as I said earlier, there is the oxidation processes, and if you oxidize methane and if you oxidize many VOCs, you get CO. That's one of the main products. So that's one of the big sources on a global scale of CO in the troposphere. And then, of course, you have the direct sources, especially biomass burning and fossil fuels, which is another big player. Both of them are changing for various reasons. You know, as methane changes, or hydrocarbon changes, then you have changes in the indirect source. The climate affects, you know, these reaction rates, as we said earlier, for example, because they depend on temperature and other things. Then OH, which drives these oxidations. It also depends on water vapor, on climate. And then when it comes to sinks, there is basically only one, and it's the oxidation of CO itself. So if you see here, there is this OH reaction, basically this one here, which breaks down CO as well, and then it removes it from the troposphere. And that's the main reason, the main way how it can be removed. Now, in terms of ozone, which is even more complex, it didn't used to be, because everyone thought until the 70s that, you know, tropospheric ozone is just input from the stratosphere, which has so much of it due to the dynamical effects, and then deposition to the Earth's surface. But then came the chemists and said, you know, it's not just that. We have recently discovered stuff in the lab, and this could have a lot of applications. And the main thing that, I mean, if you don't already know it, the main thing to point you to the main initiation process of chemical production of ozone in the troposphere is this photolysis reaction here. So if light falls onto NO2, it breaks down into NO, but it also produces a single oxygen atom, which then reacts with an oxygen molecule to produce ozone. And that's the main way how ozone is produced in the troposphere. There's a lot of things behind it, more complicated, but that's an overview, let's say. Then on the other hand, you have the removal processes, and the only removal, the chemical removal process of ozone is by photolysis. The process that I said earlier produces OH radicals is the way how ozone is being destroyed. Short wave radiation gets on it and it's being destroyed. So if you think about it,
you forget VOCs.
Yeah, but well.
Okay.
But I thought you said it was a major oxidant, so it should be reacting with things as a major oxidant.
Ozone.
Yeah.
It's not a major oxidant.
Well, it's an oxidant, so how come you don't have reactions with things?
No, it does react with other things, but compared to the other things that happen to it, it's a minor, let's say, path. The oxidation that happens with ozone, it's, yeah, if I use the word major, it's wrong. The major oxidant is OH. This is kind of a secondary.
I was just thinking of your first slide. You said it was a direct oxidant. It was directly affected the oxidation state of the atmosphere. So
yes.
I was surprised that we don't see oxidation showing up on this slide. That's all.
Oh, actually, that's what it is. I'll talk about it later. So you have, you have this, which is the main production of ozone, the main way of producing ozone, and then eventually this ozone will be destroyed. So that could be a null cycle, actually, because then there are other stuff here I won't bother you about this, which, you know, eventually don't produce ozone. But on the other hand, you have these guys here, especially in polluted environments. This is non-methane hydrocarbons, methane and CO, so VOCs and CO basically. And whenever you have these, they are getting oxidized, and they produce these guys here, which are called the peroxy radicals. And basically what these guys do is that they just recycle and NO back to NO2. And that's why they're so important, because without losing any ozone, you recycle and you get one extra NO2 that can then reproduce ozone. So the more of these guys you have, the more ozone production you can get, if that's clear. So this gives you another hint that ozone should depend on CO to some extent. Of course, it's not a linear relationship. We don't understand it completely, and that's why we're studying on a global scale. So yeah, that's what I'm saying here. used satellite data. I'll say later on how important this data set is, in conjunction with the model to constrain this ozone-CO correlation and diagnose what are the underlying perhaps processes and if the model captures them well. And this is actually a paper we now have in review. I think soon probably will be in press, which I should say hasn't definitely not answered all the questions underlying this. It has given some results, some insight, but I think there is more analysis in a follow-up that should be done in that respect, because it proved to be a very complicated problem. So, I mean, why study the ozone-CO correlation? I mean, first of all, I hope I've demonstrated how important and complex they are. And there have been several studies looking at this correlation and comparing against models. I just mentioned a few, but there have been many, many dozens. But just using surface observations and maybe some aircraft campaign data. So generally, there hasn't been insights looking at a global scale, and there hasn't been for a long time on large spatial scales. So here, actually, another thing to mention is that generally, these studies, in their own actually words, I put it here, they evaluate whether a model captures ozone correctly for the right reasons. So meaning that, okay, we see a model which, for example, over Massachusetts, captures fairly well the observations that some people measured in Massachusetts. But on the other hand, if we compare the ozone-CO correlation in the measurement of the model, and it's not comparable, it's not it doesn't look good, it implies that maybe you capture ozone correctly for the wrong reasons. So, and it's generally assumed that wherever you see positive ozone-CO correlations, you tend to have, but you should have behind it a net ozone producing region. So a region where ozone production is more dominant than ozone destruction. And actually this is good to keep in mind because we challenge it later in the discussion. I mean, the other thing is that we have data, and that's another motivation. For the first time, there is a satellite that provides ozone and CO profiles at different levels in the troposphere, on a global scale, of course, because that's what a satellite does. And ozone and CO are simultaneously measured at the same locations from the same instrument. So it's a quite unique opportunity to start looking at things like that, which we could do only in the models before, but now we can do in the models in conjunction with the observations. So there was a study, an early study that looked into a month of data and produced some of these ozone-CO correlation maps, but that was just from a month. And here we use 4 different years. We use 2 different models in order to demonstrate how it could add to their evaluation. And also we do sensitivity runs to examine the emissions role into driving these correlations. So I'll briefly say that TESS is the Tropospheric Emission Spectrometer, which is on board the AURA satellite of NASA. And that, I mean, it overpasses its location around 145. And we're using the latest version 4. And when it comes to models, we use this model, which basically is the GISS model, but with composition components, on top, like chemistry and aerosols. And a similar model in terms, not similar, but I mean, a CCM, a chemistry climate model as well, which was developed in the UK. That's a very new development with chemistry and aerosols as well. The other thing to keep in mind is that we sampled the model outputs according to the observational time and location, and that we also apply these averaging kernels which come with the test product in order to compare like with like. So this is an indication, this is a matrix which gives you a sense of how sensitive your retrieval was at particular points in the troposphere, and this is why we used in the model in order we applied this to the model results in order to simulate this kind of sensitivity in the model outputs. It's a little bit complicated if you don't already know about this thing, but I mean, we could discuss later if you want. So I'll start with some absolute concentrations, because that's what usually people do when they have a satellite and a model. They compare and see if the absolute concentrations look well. We have 2 summer months and 2 winter months. We used all the years, those 4 years, 2005 to 2008. And keep in mind that in all the things that I show from now on, we focus on 800 to 400 hectopascals, because this is a region where TESS has its highest sensitivity for both ozone and CO. Of course, that is not consistent everywhere, but broadly speaking, this is a good region. Yes?
I'm sorry, is it a limb sounder, or is it actually looking down? How is it?
Down.
It's looking down?
Yeah, yeah. So, yeah, so this is the region where we expect to have the best sensitivity, and that's why we average over that region. But later on, I'll show that it doesn't really matter exactly over which region you average, as long as you are within this middle tropospheric, let's say, domain. So here is TESS and then the two models. First of all, I'll note that you see that in all cases you have more CO in the winter, which has to do with the fact that in the winter you have less OH over this polluted regions, especially in the northern hemisphere, because there is less light to photolyze ozone and produce OH. And since OH is the main removal of CO, this is why in the winter you see more CO in the atmosphere. And you can see that this seasonal effect is being simulated in the model quite nicely. And also the distribution looks fairly nice in these models. You could say also that both models are overestimating CO pretty much everywhere, while on the other hand, there have been studies that have shown that TESS is actually, in some cases, especially in mid-latitudes, underestimating CO compared to aircraft measurements. So I mean, broadly speaking, we can say that it seems to be a fairly consistent picture with maybe some overestimations, but with a pinch of salt because there's possible TESS discrepancy. Then when it comes to ozone, it's the other way around in terms of seasonality. You see more ozone in the summer over these polluted regions. Especially you see over regions who have a lot of sunshine during that time. And that's because of more photochemistry producing more ozone. That's because you have more NO2 photolysis reactions happening. I mean, one reaction, but faster actually due to the sunlight. Again, the seasonality is pretty nicely captured in the two models. You could say that the GISS model is kind of overestimating in some areas, and the UKCA model is kind of underestimating in some areas. But again, it looks a fairly well distribution. Plus, the TESS instrument, if anything, it has been shown to have some actually positive